Okay, I'm going to do another Thiessen polygon problem. This time I'm actually going to calculate the weighted average precipitation over a watershed. So once again, here's my watershed. It's a little bit more complicated here because I've overlain a grid. Let's assume that each little square here represents this, each one of these guys here is 1 kilometer. Okay, so 1 kilometer squared, I should say. Okay, so we have the area here, and we're going to use counting to figure out the area of our polygons. So remember, the basic idea is I draw lines between our points, and then I then draw the perpendicular bisectors of those to define the Thiessen polygon. So first, here are the lines between the points in purple. And here I actually used a straight edge to the best of my ability on this tablet. I just wanted to make one other point here. There are actually only 2 stations within our watershed and 1 outside of our watershed, and we're going to consider the implications of that in a second. But notice that even though that station is outside the watershed, it's possible that its sphere of influence or its area of influence it could encroach on the watershed, and so it will provide useful data for the watershed. And in fact, that's exactly going to be the case, which is why I'm including it. And the point I wanted to make is that when you draw these Thiessen polygons, you don't have to, and you shouldn't really, just restrict yourself to stations within the watershed. Okay, so now I'm going to draw the perpendicular bisectors. And here I've just sketched them because that's sort of what I would expect you to have to be able to do on an exam or on a problem. So the lines in blue represent the Thiessen polygon boundaries. You can see, really importantly, that that station outside the watershed actually has a pretty big area of influence. In other words, all this area over here to the right is best served by measurements from that station that's actually outside the watershed. Now, I'm going to erase the purple lines or I'm going to make them lighter here so that I can concentrate on the blue ones, which are actually our polygon boundaries. And now what I'm going to do is actually count the area within each polygon. Now, there are obviously more sophisticated ways to do this, but I'm going to use this simple method here, whereas I'm going to count every square, and I'm going to make a judgment call that if the square is mostly in the watershed, I'm going to count it, and if it's mostly not in the watershed, I'm not. So starting here, this one is in the watershed. That's 1, 2, 3, 4, 5. Let's see, this one's 6. That one's mostly in. 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 20, yeah, maybe 27, 28, 29, 30, 31, 32, 33, 34. So I think I misspoke a second ago. I meant if it's within that polygon. And like I said, it's a judgment call. Some of these you might think are in or mostly in or mostly out, but it's not really going to make much of a difference. And so I ended up with, let me count again here. Yep, I get an area within this first polygon of 33, and if each one represents a square kilometer, this is 33 square kilometers. Okay, and using similar techniques, let me count up the others, and I won't actually make you watch me do it. Okay, let's see now how we might try to calculate the average precipitation within this watershed. So let's consider a bunch of methods. Let's say number 1, let's just average the precipitation values for the stations within the watershed. So we only have 2 of them within the watershed, one at 30, one at 40. So we could take the average, the regular average of 30 and 40, and I think you can do that in your head. That would suggest that the average precipitation is 35. Let's assume that those were inches. The second thing we might do is we might take the average of all 3, even though one of them is outside of the watershed. And that would be, if we go back up here, we have 130, 140, 150. 1 at 30, 1 at 40, 1 at 50. So the average of 30, 40, and 50. And again, I think you can do that in your head. We would get 40 inches. And the third, which is the best way to do it, is to use the Thiessen polygons to compute a weighted average. And the weighted average scales the influence of each of the stations to its geographic area. So what we'll need to do is create a table, excuse me, to do the weighted average, and let me show you how that works. Okay, here I've created the table and I've entered the data that we have observed. So we have three stations, A, B, and C, and the precipitation at station A was 30 inches and it had an area of 33. So going back up here, that's the one in green, right? That station had precipitation of 30 inches and it covered that area shown in the upper left, which I've shown in green, and had an area of 33 kilometers squared. And I do the same thing for the other two Thiessen polygons. So there are the data we have observed, the precipitation and the areas. Now, the next thing we want to do is calculate the total area of our watershed, and we can get that simply by summing up these three values there. And the sum is equal to 130 square kilometers. That's the area of our watershed. Now, what we want to do is calculate the percentage of the area of the watershed for each of these three Thiessen polygons. So to do that, what I'll do is I'll divide, let me do this in a different color here, I'll divide the area by the total area to get a fraction, and I can express that as a percent. So for example, the first one, the area, the weight, we call that the weight, will equal 33 divided by 130, and that's equal to 0.25 or 25%. So I'll put 25% here and calculate the others exactly the same. And one thing you can always check is that your weights should all sum up to 100%. And if we do this right, 40, 75, there you go. They sum up to 100%. That means we've calculated them correctly. Now, the final stage where you can actually get the weighted mean is we are going to multiply the weight for each Thiessen polygon, the weight times the precipitation. And I'm going to write that into this column called contribution. This is the contribution to the total precipitation, average precipitation of the watershed from that polygon. So, for example, the first contribution will be equal to 30 inches times 25%, which is 0.25, and that's equal to 7.6. So that's actually in inches as well. And we're going to do the same thing for Thiessen polygon B and C. And finally, we're just going to sum up those contributions to get our final answer, which is the weighted average precipitation over the watershed. So I'm going to sum up 20, 13.8, and 7.6. And I get the weighted average, and this is my final answer here, of 41.4 inches over the entire watershed. And that's really the best estimate of the average rainfall over the precipitation over the watershed. You can see it differs a little bit from the others. If I averaged all three, I think I got 40, and if we just averaged the two that were within the watershed, we got 35. But the best estimate, which takes into account the distribution of the areas served by the stations, or rather the areas of influence around each station, is the weighted average, and the weighted average in this case is 41.4 inches per year.